In this video, I'm going to demonstrate how to use the Enki software ecosystem running on the cloud server to run some MELTS calculations. For those listening who are new to MELTS or do not know what it is, MELTS is a thermodynamic modeling package used to calculate phase stability in magmatic systems. Please visit the URL melts.ofmresearch.org for more information and context. There are two ways to perform MELTS calculations using Enki. This video illustrates the simplest calculation method, which is appropriate for simple modeling applications, for teaching exercises, and for an introduction to the capabilities of this modeling software. A follow-up video will introduce MELTS modeling in the context of a more advanced modeling infrastructure that uses the Equilibrate class of the ThermoEngine Python package. To get started with some basic MELTS modeling, let's log into the cloud server and navigate to the MELTS pMELTS subfolder found in the Notebooks collection. When running a MELTS simulation, there are 4 thermodynamic model database collections that may be chosen. It is important to choose carefully in order to get the best results for your modeling application. Use version 1.0.2 for standard MELTS models at low pressure, that is less than 1 or 2 GPa, and on bulk compositions corresponding to naturally occurring magmas, basalts to rhyolites to peralkaline lavas. Version 1.0.2 is commonly called rhyolite MELTS, although this version is equally applicable to mafic liquids and is 100% compatible with the original MELTS model calibration. With respect to the original, rhyolite MELTS has enhancements to extend that calibration to silicic systems characterized by the 2 felspar quartz water-saturated ternary minimum. Importantly, the version 1.0.2 model does not extend to carbon dioxide bearing systems. Use version 1.1.0 for calculations in silicic systems characterized by the 2 felspar quartz water-saturated ternary minimum, that is, for rhyolites, that are CO2 bearing. Do not use version 1.1.0 for phase equilibrium calculations in other contexts. Use version 1.2.0 for CO2 bearing systems and for bulk compositions other than those that generate a 2 felspar quartz water saturated ternary minimum. Version 1.2.0 contains the most comprehensive water solubility model and can calculate mixed fluid saturation in mafic, intermediate, and alkalic bulk compositions. This model can also be used to calculate accurate water, carbon dioxide, mixed fluid saturation in rhyolitic systems, but it cannot retrieve the temperature, pressure, solid phase saturation conditions of the ternary minimum. The pMELTS model should only be used at pressures greater than 1 gigapascal and less than about 4 gigapascals. It is only applicable to mantle-like bulk compositions, that is, peridotite and peroxenite. The pMELTS model was developed and optimized to describe mantle phase equilibria below the spinel-garnet phase transition. Now that we know a bit about which MELTS modeling framework to use, let's do a simple calculation describing the equilibrium closed system crystallization of a high silica rhyolite. Let's start by opening up the MELTS 1.0.2 equilibrium notebook. This notebook, like all Jupyter notebooks, consists of documentation cells and code cells. The first code cell, importantly, imports the equilibrate module from the ThermoEngine Python package. Let's execute that cell. The second code cell instantiates an instance of the MELTS modeling class, MELTS model. By default, the MELTS model that is instantiated will be version 1.0.2. We'll see in other notebooks how to instantiate other versions of MELTS. The third cell provides a means of accessing what oxides are known in the MELTS package for specifying a bulk composition and what phases are known in the MELTS package. By default, printing those oxides and phases is turned off, but let's turn it on and execute this cell and get a list of all of the oxides that are known to MELTS and the order in which they must be specified, and a list of all the phases that are known, both pure phases and solid solution phases. We'll have need of this list a little bit later on. The next importance code cell specifies the bulk composition that will be used in the MELTS simulation. Here, the composition is a high silica rhyolite. This happens to be an example of a bulk composition from the late Bishop Tuff. Now we'll consider one of the first things that must be done in specifying a MELTS simulation, and that is whether all the solid phases that MELTS is capable of evaluating should be included in that calculation. We specify whether or not phases should be included by suppressing phases. By default, all phases are allowed to precipitate. This little code block here is used to suppress the crystallization of nepheline and orthorhombic oxides. We didn't need to do this, but this is an example of how phase suppression can be done. We'll use phase suppression in one of the last notebooks we examined today. To do a MELTS calculation is very simple. We simply invoke the equilibrate TP method of the MELTS instance that we created above. The equilibrate TP method takes as arguments a temperature in degrees centigrade and a pressure in megapascals, and some information as to whether or not this is the first time the package is called. Initialize equals true means this is the first time the package is called. The output of the calculation will be sent to the Python output variable, and that Python output variable consists of a tuple, which is the status of that calculation, the temperature and pressure at which the calculation was done, and a variable that contains XML output of all of the results of that calculation. We see that the calculation was done successfully at the temperature of 760 and 175 megapascals. Now, to retrieve information about the results of a MELTS calculation, we use a number of methods that are available in the MELTS model class. Probably the simplest thing that can be done and the most useful thing that to be done is simply to output a summary of the calculation. What the output summary method does is read in the XML out file and extract from it information as to the equilibrium state of the system. You can see that at this temperature and pressure for this bulk composition, the stable assemblage is quartz, liquid, sanidine feldspar, and water. Other information can of course be extracted from the calculation results from the XML out string, and a number of methods exist to do that. Probably one of the more useful of those is the get property of phase method, which is illustrated in this next code cell. And here we've extracted the thermodynamic properties of the system. Another useful thing to examine from the MELTS calculation is the calculated chemical affinity of all of the phases in the system. Chemical affinities, if you do not know, are estimates of the degree of undersaturation of a phase with respect to the stable solid liquid phase assemblage. The chemical affinities will be positive for all those phases that are undersaturated in the system, and the degree to which they are positive is a measure of the degree of undersaturation of that particular phase. For all phases, a chemical formula will be returned that describes the composition of the phase which is closest to being in equilibrium with the system. The last cell of this notebook illustrates a way to do a calculation of a sequence of equilibrium steps along a pressure constant, temperature defined path. Most of the code in this cell has to do with setting up phase selection for plotting and for defining the characteristics of the graph on which the results of this calculation are going to be displayed. Important parts of the code are contained in this loop, in this for loop right here. And the most important part of the code is calling the MELTS underscore TP method repeatedly for a series of temperature increments. Output is then broken down, and important results of the calculation are saved to plotting variables. This code block also illustrates how results from the MELTS simulation can be stored in an Excel notebook, which can later on be output and downloaded to your local machine for further analysis. Let's execute this cell. And we see that the sequence of MELTS calculations are done in descending temperature order, and results are plotted. The next notebook to look at is the MELTS 1.02 fractionation notebook. This notebook illustrates how to perform fractionation calculations, in this case using MORB as an input bulk composition. Compared to the previous notebook, much of this notebook is identical. The first cell that imports the equilibrate module from the thermoengine package is exactly the same. The second code cell that creates an instance of the MELTS model class is exactly the same. The third cell interrogating the oxides and phases that are used by MELTS is the same. The fourth cell is different because we're specifying here the composition of a mid-ocean ridge basalt rather than a high silica rhyolite. The fifth code cell, again, is the same as in the previous modeling notebook, where we suppress nepheline and orthorhombic oxides. And in fact, the first equilibration step is exactly the same as the previous notebook. We're simply establishing at some initial temperature and pressure the equilibrium phase assemblage. In this case, the temperature and pressure is 1220 degrees centigrade and 100 megapascals. We can also output the equilibrium phase assemblage at this initial temperature and pressure. And again, there's really no difference between this code and the code of the previous notebook. To do fractionation, here we have our first difference. We need to specify fractionation coefficients for all the phases in the assemblage. Now, what are fractionation coefficients? Fractionation coefficients are simply the degree to which a solid phase, if produced, is fully removed from the system. A fractionation coefficient of 1.0 means that if a phase is produced, as an example, suppose augite is produced, it will be fully removed from the system at each step in the equilibration process. So fractionation is hereby modeled as a series of equilibrium steps with phases removed at each step in the sequence. The extent to which those phases are removed corresponds to the fractionation coefficient. We'll leave the fractionation coefficients with a value of unity to have them fully removed at each step. The last cell in this notebook, as in the previous notebook, simply runs the series of equilibrium steps with the important difference, which can be seen here in the loop, that at each stage of the simulation, the phases are fractionated from the previous step, fed into this fractionation output variable, and the extent to which they're fractionated is defined by the fractionation coefficients. We can run the simulation. and we produce a graph of the composition of the liquid as a function of temperature resulting from the fractionation, the full fractionation of solid phases at each step. As in the previous notebook, results of this simulation are also extracted and written to an Excel workbook that makes them available for download and analysis on your local machine. One last notebook that we will look at is the pMELTS version 5.6.1 adiabatic notebook. Let's open that. This notebook illustrates how to use the pMELTS model and a peridotite bulk composition to simulate adiabatic melting of the mantle along a pressure gradient. This calculation utilizes an entropy-conserved path to simulate reversible adiabatic decompression melting. In this simulation, an initial temperature and pressure are chosen, and the entropy of an equilibrium phase assemblage is calculated. That entropy is then held constant, and temperature is calculated along with phase compositions and proportions by varying pressure while minimizing the system enthalpy. You should recall that the enthalpy is the thermodynamic potential that is minimal at fixed entropy, pressure, and bulk composition. Let's open the pMELTS 5.6.1 adiabatic notebook. The first cell of this notebook, again, is identical to the previous ones, simply importing the equilibrate module from the thermoengine package. The next code cell is a bit different. Unlike previous notebooks that we've examined, this code cell creates an instance of the MELTS model class specifying the version of MELTS to use. This is the 5.6.1 version, that is pMELTS. The next code cell outputs oxides and phases, if desired, to see what oxides and phases are used by pMELTS. And the next code cell specifies the bulk composition of the system. Again, since we're using pMELTS, this bulk composition is in this case a peridotite. The next code cell specifies the suppression of phases known to pMELTS, but of no interest to the results of this calculation. For example, actinolite is unlikely to be a phase participating in mantle melting of peridotite, or as is corundum or cristobalite or cummingtonite. And these phases are simply suppressed in this call from resulting in the calculation. If we execute that cell, that suppression is indicated. Whenever doing a modeling calculation, if you are sure that a solid phase is not going to participate in the final equilibrium assemblage, it does save considerable computer time by suppressing that phase at this stage before invoking the model. The next cell executes the usual equilibrate step at known temperature and pressure. In this case, we're choosing 1300 degrees and 1000 megapascals as the initial temperature and pressure. 1000 megapascals is a gigapascal, by the way. And the results of that calculation can be summarized by executing the next cell. Note that the assemblage is very, very close to the solidus, and I've chosen the temperature on purpose to be very, very close to the solidus. Having found the equilibrium phase assemblage at the input temperature and pressure, the next cell does something rather different than previous notebooks. In the next cell, we retrieve the total entropy of the system that resulted from the calculation performed in the previous cell, store that entropy in a variable called S, and then use that entropy to reestablish the equilibrium state at fixed entropy and pressure. Now, equilibrium is equilibrium. So whether we specify equilibrium at fixed temperature or pressure or fixed entropy and pressure, we should get exactly the same answer. And the results of that calculation are shown to be identical to the previous one, as they should be. So this cell is executed mainly as a check to make sure that there's nothing wrong with the software and with our computation of the system entropy. Having found the entropy, we now know the total entropy of the system. So we can now run a simulation along a path that corresponds to constant entropy and varying pressure. And this will be an adiabatic melting path. This little code block here simply does that. Again, much of the code corresponds to simply deciding which phases to plot up, which phases to keep track of. The main loop is done here, where the MELTS class method equilibrate at fixed entropy and pressure is called. And the entropy is held constant, that is, the entropy increment is set to 0, and the pressure is incremented to look at adiabatic melting along this pressure varying path. If we execute the cell, we'll produce a sequence of melting reactions along that pressure gradient, going from 1,000 megapascals all the way down to 50 megapascals. And the results are plotted here in terms of phase assemblage versus pressure. One of the different things about the graph of simulation results that you see here is that I've also included a graph of the temperature of the system, which is the solid black line here, as a function of pressure. And notice that the temperature of the system is not a linear function of pressure, as you might suspect from a typical geothermal gradient. This temperature is calculated at each step corresponding to the adiabatic condition. And the fact that it is nonlinear and has fluctuations has to do with the entropy conservation constraint and the phase assemblage and proportions that are being crystallized. That's the end for this video. We'll leave the other notebooks in this folder for you to examine on your own. In the next video, we will look at MELTS-like calculations performed using the more flexible equilibrate class of the equilibrate module. I hope to see you next time.